So, do you see my blackboard now? This is
Yes,
last
we see.
time. Yeah.
Yeah.
So let us quickly review last time's lecture, and you ask any questions on last time's lecture at the end of that review. So last time we talked of topological space and continuous map and Hausdorff property and examples of that. So we talked of the product of R with itself, and these are the two directions of the binary product. It sends an order tuple to X and order tuple to Y. And the universal property is if there is any Z with one continuous map to F and another continuous map also, to R and another continuous map G to R, then that induces a map from Z into R cross R, which sends any Z to Fz comma Gz, and this is a continuous map. And this is the only continuous map making that diagram various triangles come out, meaning go to R cross R and then go under the first projection, that should be F, go to R cross R and go to the second projection, that should be G, which it is the way we are constructed. First projection is indeed F, second is G. And then we did some very, very important examples of continuous maps. All of mathematics is built on these maps. The first one is addition, primary school, back to primary school. Addition is a continuous map on reals. You didn't have reals in primary school. There it was only integers and which has discrete topology, so everything is continuous, no problem. So you know this fact, by the way, that if X is a discrete space and Y is any space, then any map from X to Y is continuous. You know this? If you don't know, then the tutors please note and ask somebody to prove it in a tutorial. Okay. Next was multiplication. Multiplication map is also continuous map on R cross R, which sends X comma Y to XY. Then minus is continuous, or a constant map is continuous, or 1 upon X is continuous, but then the domain you have to take to be R star. Now, here this R star is a subspace of R. And so I remind you, I told you what is subspace topology. If I have topological space, X comma T, X is the set of points, T is the topology, and Y is any subset of the set of points, then I get a topology on Y. Namely, define a set to be open, all those which are intersections of open sets in X with Y. So U is open in X, which means U is a member of T and intersected with Y, you get open subsets of F. Then this is also topological space and this is a continuous. It's called subspace. Yeah. Today we will talk about subspaces in some more abstraction. So then for constant map, we said any constant map is continuous. Any topological space, any other topological space, any point there, and the constant map sending everything to that point is continuous. Then we talked of examples of topological spaces. One was empty space, another was singleton space, third was real line with this metric, usual Euclidean metric. Then by product, you get all these spaces. Then this is a subspace, very important, as we will see later. This is compact. You have already encountered this subspace you have met again and again in your calculus class and so on. Its products with itself, which we will again see, are compact. Then we introduce the circle. Circle we introduced by this equation. And then I asked you to show that circle is closed. At that point, we gave two proofs. The first proof entirely relied on these basic exercises that addition, multiplication, constant, etc. are continuous. And then this map X comma Y going to X square plus Y square minus 1 is built up of one multiplication of X with itself. And that comes from a projection. First take XY to its projection X. Projection map is continuous, then square map is continuous, composite of continuous is continuous. So X square is a continuous function on X comma Y. Similarly, Y square is a continuous function. Therefore, one continuous function into R, another continuous function into R, which means I got a continuous function into R2, sending X comma Y to X square comma Y square. Now add those functions. So I get this one. Similarly, the function 1 is, or minus 1 is continuous, 1 is continuous, minus is continuous. So this is a continuous function. This we proved simply by using continuity of those basic functions and decomposing this function as made up of those. The other proof directly looked at how a circle, what's the appearance of a circle. So if I point away from it, I can take a tiny ball away from the circle. So it is open. This looks very intuitive and obvious. This looks like you can, it's built up of much smaller, simpler things. So if there are many examples where geometric intuition is difficult to obtain, higher dimensional and whatnot, or you may be more algebraic minded, depending on whether you can see the things or whether you want to break them down into the components. You give any of the proofs, give both. Lucky is the person who can give both proofs, but use any one to help your intuition on the other side. Okay. Then we talked of Hausdorff, and we said that, I reminded you that Hausdorff means the diagonal is closed. This is an equivalent formulation of Hausdorff, and this was an illustration. This line is closed, and this is a little box U cross V, which is open in the topology of product and doesn't meet the box because of this property. Here, every point of the diagonal is a double point, x comma x, and diagonal of y is y cross y intersection x cross x. This shows that if I have space x and a subspace y, and if x is Hausdorff, then y is also Hausdorff. Here it is. This is close x Hausdorff, y is Hausdorff. Then I told you that product of any two Hausdorff space Hausdorff, that was an exercise asked you. Yeah. If both are non-empty, then converse is true. Also, if both are empty, then also converse is true, because empty cross empty is empty. But if any one of them is non-empty, and then this is true, converse is true. Then we continued with examples, and I gave you the example of S1 cross S1, which was a torus. Then I told you that if you have clock and the hour hand and the minute hand, then the position of the hands determines a point on the torus, because there are two angles involved, and a point on a torus is given by two angles. One angle is for the circle going around like this, another angle is for the circle going around like this. And therefore, the path of the clock is on this torus. And when this goes around once, this goes around 12 times, which is why the path is like winding a wire around some solenoid. In electric circuits, to make electromagnets and whatnot, you wind the wire around a piece of iron. It's like that winding. And I told you that topological spaces are the stages on which the drama of mathematics takes place, like the drama of clock moving takes place on this torus, and that's why we study. Okay, so that was a quick recap of my last lecture, and it took 10 minutes for the recap. Not bad. So at this point, any questions? As usual, I'll wait 10 seconds for you to ask your question. Gather your courage. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, there are no questions. So now my next question is simply designed to make sure that my mic is on, my internet connection is on. So are you able to hear me?
Yes, sir.
Yes, sir.
Yes, yes.
Yes, sir.
And you know, this is a question where if you had answered no, the meaning of the answer would still be the same. And then I'll ask, oh, you still don't hear me? And you say, yeah, we still don't hear you. Then, you know, it gives the same information. So sometimes a sentence and its opposite can give exactly the same information. Here is a case of that. But, well, let's not talk about that. Next month, I have to give a course on logic. That's where I should make such things. Okay, now, so today I want to talk about subspaces, embedding, quotient, quotient maps, examples. So let's begin. What color should I have for this? Black is okay. Okay, so I'm going to tell you a particular thing, that I have special kind of map. Let's call it F. F is a map from Z into X. Both are topological spaces. Continuous map. And suppose it has two properties, three properties. One is it is continuous map. Now suppose that F is injective. Okay, this is the second property. Continuous map we want, of course, we want continuous. This is the second property. Okay. Now let me pause at this point. Suppose I had two groups. I had a group G, I had a group H, and suppose it had those two properties. F is a homomorphism. These are groups. These are topological spaces. And suppose the second property is F is injective. Then at that point of time, you'll say, yeah, that makes H a subgroup of G. This is an embedding. Then you say that F is an embedding. Okay. F is an embedding of H into G. So where does the word embedding come from? You know jewelry. So there is a ring, suppose. Now this ring is the one you wear in your fingers. Okay. The ring looks like this. And all this is made of, let's say, silver, whatever. And then there is a ruby. And the ruby is embedded. Okay. So I'll say this gem is embedded in the golden ring. This is the way you might have seen the word embedded outside mathematics. So I take it you are familiar with the word embedding. Okay. So if I have group H and an injective homomorphism to a group G, this arrow has come out to be very bad. Let me make the arrow look better, more like an arrow. Okay. Then this gem is embedded there. Okay. You take the gem and you put it in the ring. You are taking the ruby and put it in the golden ring. G is the golden ring, H is the red colored stone, and F is the putting it in. And you have put it in injectively. Okay. Now it has becomes there. So in groups, all that you want is F is a homeomorphism and F is a homomorphism and F is injective. But here we need a third property. The third property needed is F is a homeomorphism or induces. Is means induces. Is a homeomorphism of Z with Fz, which is the image of Z, image of F, where Fz in X is given the subspace topology. So this is my property number 3. F is a homeomorphism of Z with Fz. So if these three properties hold, then I say that if F Z to X satisfies 1, 2, 3, then we say that F is an embedding of Z into X. So I have finished telling you the definition. And here there is no third property required because automatically F will be an isomorphism of the group H automatically its image is a subgroup of G. Here in contrast. So in contrast, so different color. Automatically FH is a subgroup of G. So 1 and 2, 1, 2 imply, okay, automatically. What's automatically? I should say 1 and 2 imply. After all, I am making some assumptions. So 1 and 2 imply FH is a subgroup of G and F from H to FH is an isomorphism of groups. So you guys know this is true, right? Once I have an injective homomorphism of groups, once I have any homomorphism of groups, its image is a subgroup. And now once I have an injective, now this is an injective map from H into its image. And therefore, it's being a homomorphism and being injective, it's an isomorphism. This is because, therefore, this is simply because the following basic property of groups. In groups, any bijective homomorphism is an isomorphism. So you see, this is a bijective homomorphism. It is injective and it's surjective because I have now, instead of G, I have simply taken the image of F. Anything is anyway going into its image. So this is a bijective group homomorphism, therefore an isomorphism. This property, now I ask you, if this property was true for topological spaces, I won't need this property number 3. But it's not true, so I have to also assume this. This is an important point. So make sure you understand what I'm saying. So I am going to ask you a question. So here is the question. Let G from X to Y be a continuous map of topological spaces such that G is a bijection. Is G a homeomorphism?
Can I answer?
So somebody wants to answer?
Yes, please.
Yeah, answer. Tell your name and answer.
Ishan, no, it's not. Take X.
Sorry, I didn't hear your name again.
Ishan, can you hear
Ishan,
me?
yeah,
Yes.
I can hear you.
Take Y being X itself,
Yes.
and G being the identity map.
Right.
And X you equip with the discrete topology.
Yes.
And Y with the indiscrete topology.
Yes.
And you need X non-empty in this case.
That's not enough. Ishan?
Yes,
your
sir.
idea is great, but you missed out one possibility. They could be singleton.
Okay. Oh, yeah, of course. Yes, of course.
Good.
It cannot.
Okay, all right.
It has to have at least 2 points.
Yeah,
yes.
all right. So enough. So as Ishan has described to you, you may have large set having 2 or more points and give it the discrete topology, call it X. Give it the indiscrete topology, call it Y, and take the identity map. Then of course it is continuous because, as I told you, any map from a discrete topological space to any topological space is continuous. So this is of course continuous and it's a bijection, but it's not a homeomorphism because the inverse map is not continuous. In other words, the map is not open. If I take any open set here, say a singleton point, its image there should be open if the inverse map is to be continuous, which is not so. Okay. All right. Therefore, you see that this requirement is not automatically fulfilled, because if f z to x was such a map that z is the same topological space x, but now put the discrete topology, then this map is indeed bijective and continuous and injective, yeah. But then it's not a homeomorphism with its image, because its image is all of x. Huh? So this example shows that this third condition is not automatic. Has everybody understood this point? Why I have to put by hand this third condition? You also understood how it is different in groups. So you see, these categories have certain different behaviors, a lot of different behaviors, even though there are a lot of similarities being categories, but there are a lot of differences also, which can also be explained in categorical terms. These are extra properties of the category which they don't necessarily share. So this is why now I have defined embedding. Yeah. So is the definition of embedding clear? As I told you, I want plenty of examples. So let me begin with an example. After all, I have some topological space. For example, let's take R. And now take x cross x and take the diagonal map of x into this. Here I can draw a picture. That's going to be the map from R to R cross R, whose graph looks like this. So this R, let me draw in color pink. This is this R. And then this map is putting this R here like this, because this is the map which sends small x to x comma x. This is the diagonal map. So now tell me, this diagonal is, so therefore I get a map. Let's call this diagonal as diagonal of R. So this induces a map delta from R to diagonal of R. Diagonal of R is this pink line here. Is this a homeomorphism? It is sending x to xx. Yeah, somebody answer. Is this a homeomorphism?
No.
No? Why not?
Because it's homeomorphism is in particular a bijection.
Yeah, so why isn't it a bijection?
Because it's only taking points x comma x. So if I take 5 comma 6, it's not there.
But I'm not asking whether this delta is bijection.
Oh, you're going to delta R. Sorry, I thought you were going to R cross R.
No, so I have given it the same name, but you might call it delta prime if you want.
No, that's okay. Sorry, I did not notice that part.
Yeah.
So this is going to be a homeomorphism, because
exactly.
I mean, we can project it back.
Correct. So, so this was Ishan again. Who was it answering? Projecting
Not
back.
me,
Who
sir.
said that?
Sir Himanshu. Yeah.
Himanshu. So Himanshu, you have given a great answer. You realize that your answer is very general. You said projected back. That tells you how to deal with this. So now let's take the induced map from X. Let's call it delta prime, because now its codomain is different. It's going to delta X. Again, by the same formula, X goes to X. This is a diagonal map. This is a homeomorphism. And Himanshu just gave us the proof. The proof is I go, so let me repeat his proof in this context. So here there are these two projections, right? Here's the projection P1 and here's the projection P2. So tell me what is R to this diagonal map R cross R to R first projection. What is the composite, Bolo? Well, write the formula. This sends x comma y to x, and this sends any t to t comma t. So पहले इधर जाओ, बाद में इधर आओ. So x goes to x. This is identity. Identity of R. Huh? Or since this also shows that the map which actually lands in delta R, and we call this map delta again, but you call it delta prime to give it a different name to be very finicky. If you don't want to call it P1 because P1 had this as the domain, call it P1 prime. We will do what is called abuse of notation. We'll keep our notation simplified by using the same letter when the meaning is obvious. So what is this composite, Himanshu?
Yes, sir. So this will be the identity on the.
Correct. So now when I have x going to x cross x, this is the diagonal map, and this is the projection P1. This composite is identity. So this also means that x going from this map to delta of x, and this is P1 prime if you want to call it that, then this composite is identity. So we have shown that P1 prime composite this delta prime is equal to identity of x. Is that enough to say that this is a homeomorphism? What does being an isomorphism mean? This has supplied it what kind of inverse? It has supplied it a left inverse, right?
Yeah.
Now I want a right inverse. So somebody give me a right inverse. So I want the map to go from delta x toward x. This is the first projection. And now I want to go back to delta x. How should I go?
The diagonal.
Diagonal again. So here a point x comma x is going to x, and x is going back to x comma x. So this is also identity. So delta composite P1 prime is also identity x. And therefore, delta prime, as we called it, going from x to delta x is an isomorphism. Now I want to point out something very simple. See, you may use R and viewing this line and projecting it to help your intuition. But after you write the argument, you see the argument is entirely categorical. What did we use? Existence of the product with itself. And therefore, in any category where you have product of x with itself, the diagonal is going to be an isomorphism on quote unquote image, provided you can define an image. And this requires more work. But you see, this argument is very general. So in all kinds of things where you do have the notion of image, this argument will work. You don't have a nice notion of image in all categories, as you will learn as you go on to more and more interesting things.
Excuse me, sir.
Yeah. What do you want to know?
I'm not sure you don't have an idea of image in all categories. So I understand you're talking about that kernel of the co-kernel, but there's a simpler version which I believe works.
Yeah, and what works in any category?
Yeah, so you say that you have a morphism X. Can you draw, please, from X to Y?
Who is talking? This is Ishan.
Yes,
Who
sir.
is it? So Ishan, no.
Yes, sir.
Instead of wasting everybody's time, let me tell you that some more things are needed for that kind of things to work. Okay. And so, for example, if you have schemes, you heard of schemes, I'm sure.
Yes, but I
don't know anything. There is no
about
good notion of image, for example, in schemes, and so on, so on, so on. So you may try to make an abstract argument, but for that you will need to know more category. It will only, will take up time. But you are welcome to discuss this with me, and we will pursue this. Okay.
Thank you, sir.
All right. So you understand that diagonal is therefore an embedding. So this is our conclusion is in topological spaces, diagonal of x to x cross x is an embedding. which, let me remind you what we are talking about, gives an isomorphism, means homeomorphism in our category, of X with image of delta. Okay? And this argument will work in any categories where image is an appropriate object with appropriate properties formulated appropriately. So all this requires, so let's not go into that generality. So we already understood the notion of subspace and embedding. So this was subspace and embedding. So if you simply have X topoical space and Y is a subspace, then the inclusion map Y included in X is an embedding. Yeah, this you know in all different kinds of setups. For example, if I have group and I have subgroup of the group, then the injective map from the subgroup into the group is a homomorphism, and it is injective, so it's an embedding. There you don't need any third requirement. In groups, only two requirements, okay, because of this property. So with this, I explained to you what is an embedding. Now I am going to kind of flip the things around. If we were more categorical, you will see that what I am doing is reversing all arrows. And I am going to define a special kind of map, which I'll call a quotient morphism. Quotient map. So I'll say that X to some Y is one continuous. See, there is nothing without continuous. 2 surjection. So in our category, all arrows are supposed to be continuous. That's all. Second, it's a surjection. Surjection is kind of opposite of injection, if formulated correctly, category. And the third property says this. Here's the third property. Third. So by the way, let me remind you what continuous means. So this continuous means if is open, then F inverse V in X is open. So I'm going to take this property and turn it around. And I'm going to say, if V is in Y such that F inverse V is open in X, then V should be open in Y. So you see, I have just turned this property around. So therefore it becomes any V in Y is open if and only if its inverse image in X is open. So I can combine this continuous and 3, I can combine them into saying just one statement. That combined statement I'll make here. So combined statement will say if and only if F inverse V contained in X is open. This is one property, and the other property is F is surjective. F is, oh, I forgot to give this a name, F. This was F. F is surjective. So see these two properties, this and this, or these three properties. That is what defines a quotient map. So we are given a definition. Now we will give plenty of examples. Plenty. Okay. I'll keep on giving you examples of this. Okay, I need a new page for that. So here's an example. Here's R2, and here's the projection R. Where does this go under the first projection? Goes to X. So let's draw a picture. The R2 looks like this, and the R looks like this. This is R2. And the projection, let's give the projection map red color here. This is the projection. So here's the map, E1. So if I take any point here, let's call it X, what lies above it? What lies above it is something like this. If I take this other point which I have painted in this color, what lies above it looks like this. If I take this map, this point here, what lies above it is like this. So you see the points which lie above start looking like these threads. No? They are these threads. These threads are going down. And each of these threads is going down to a point here, point here, point here, point here, point here. Okay? So these are called the fibers. Fiber. For a long time, people wrote the spelling as F-I-B-R-E. But anyway, English is not my language and not the language of our country anyway. So you use whatever spelling. F-I-B-R-E might be what the dictionary may recommend. So write that. I have no insistence on the spelling. So it's called the fiber over X. This is X and the fiber is over it. This is the fiber over X. So is this picture clear? Why it is called fiber pictorially?
Yes, sir.
Now people were not drawing such pictures once upon a time. Okay. The first person who started drawing this picture, such pictures, name was called Bolo. What was his name? You should know some history of mathematics. What was his name? Correct. His name was Alexander Grothendieck.
Ah, Grothendieck. But really, sir, Grothendieck drew pictures
like this. Well,
oh, okay.
These are not really pictures. What Grothendieck would write is he'll write X and he'll write Y and he'll write F. This is the picture he drew on his blackboard. All his lectures in those days will begin by first drawing this. You see, we have been drawing here X, Y, right? F. He'll say, no, no, no. You draw it like this, vertically. In fact, people didn't even write F, X, Y. Even this much notation is not there in old books. Yeah, you go look at lots of old books. You will never see such a picture there. They will simply say that f is a function. They will say f of x equal to blah, blah, blah. They'll give some such formula. They won't write this like this. Okay. Grothendieck's name has got wiped out. So let me repair that. So one of the exercises all of you have for today's tutorial or whatever is read a biography of Grothendieck from the internet. So this is one of the greatest mathematicians ever. Like you guys no doubt know the name of Pythagoras, Euclid, Newton, Gauss, Riemann, blah, 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 blah. This is in that series of that class, okay? And he died about 5 years ago, so sometime, or maybe about in the last decade, okay? So read a biography of Grothendieck and okay, so going back. So these are called fibers. And I have this map from R2 to R whose fibers. So if I take x cross y and take a map to x, the fibers are copies of y. Is that clear? If I take a product of two different spaces. So this is x cross y. And if I project it on y as the first projection on x, then the fibers F inverse of any x is homeomorphic to y. Is that clear to you? The way subspace topology is defined, okay? So y to x cross y, sending any chota y to x0 comma y. Let's call it as the embedding defined by x0. So given any x0 belonging to x, define this is an embedding. So all these fibers are copies of y. Per small x0, I have a copy of y. That copy consists of all x0 comma y. So F inverse of, not F inverse. This I call Px. Oh, right. I keep changing my names. Okay. So F inverse of x0 equal to the set of all x0 comma y, such that y belongs to y. And this is isomorphic to y. Okay, and I just now gave this isomorphism. The inverse of this isomorphism is the second projection on y. Second projection of x cross y to y. So that will send this to small y. So is this example of embedding clear? I said anytime you have a product, you have lots of embeddings. The fibers are all embedded. Is this example clear? Okay. So diagonal is embedded, fibers are embedded. Now let's give you one more example. Okay. So suppose I don't know that, okay, but I think, no, you get the idea. There's no point giving more and more examples of embedding. So let's turn to the second concept that we defined, which was that of quotient. I have defined embedding. Now I am going to define quotient. Where did I define quotient? Here is quotient. So let's recall what is meant by quotient. So let's turn to this and convert it into an example of quotient. So my question. Is P1 going from R2 to R
Hello. Hello.
Yeah. Hello. 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 Hello.
Yeah, yes, sir. So,
Yeah. Yeah. Can you
okay.
see the blackboard also, or no? I have to share again.
Not still.
No,
But,
sir, it is not.
Now, do you see the blackboard?
uh, not yet, sir.
Okay.
No,
Okay.
sir.
So I have to restart the sharing. Okay. Now, do you see the blackboard?
Yeah, yes, sir.
Yeah. Okay.
Yes,
So
sir.
let's take the projection from R2 to R, which sends x comma y to x. So is this a quotient map? So let's check this. So everything is about this projection. R2 to R, for this projection, we said the fibers are embeddings. Now I am asking whether the projection itself is a quotient. So what are the properties I have to verify? First property I have to verify is P1 is surjective. Yes or no? Is P1 surjective?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. It is surjective because the other copy is non-empty. X cross Y to X, Px is surjective if Y is non-empty. Because then I can always take a point X comma Y0 and that will go map to X. I'm not saying if and only if. Y can be empty, X can be empty, and then this map is again surjective. Okay. So answer to the first one is yes. And the second requirement, combined requirement, was V contained in R is open if and only if P1 inverse V contained in R2 is open. So for that you have to say yes or no. Bolo, yes or no. So of course P1 is continuous.
Yes, it is open.
Therefore, if V is open, then F inverse P is open. Now about converse, let's draw a picture. So here is R, here's R2, and I'll take a red colored V, here's some V, and then its inverse image is this. And suppose this is open. I want to deduce this is open. How will I deduce this is open from knowing that this is open? You have intersected with the diagonal, right? Diagonal is a copy of this, and because this is open, its intersection with the diagonal is open, and that maps homeomorphically to this. Clear? So I intersected with the diagonal. This is the diagonal, and its intersection with the diagonal is this. And this part maps down homeomorphically to this part. You agreed that the projection of the diagonal on the factor is a homeomorphism. And therefore, this is open, its intersection with diagonal is therefore open, and that projects to the original one. Therefore, the answer is yes. In this particular case, you can make, because it's also non-empty, etc., etc., you can make one more argument. This line is a copy of R, right? It is of the form x comma y0. So its intersection with this line is open because this set is open, its intersection, this line is open. And this intersection is a copy of the original V, right? So if I take an original V, then I built this whole rectangle over it, and then I intersect it with a horizontal line. What do I get? A copy of the original. So the answer is yes. And therefore, this shows that T1 R2 to R is a quotient map. Is this argument clear? Any questions on this argument?
So how will we prove this using algebraically?
What do you mean prove it
Algebraic arguments.
algebraically? This was entirely algebraic argument. This argument was entirely algebraic.
No,
Yeah?
for the converse part you gave the geometric proof.
No. I use the diagonal. That's all. And all diagonal arguments were just made in terms of that. I drew pictures to illustrate for you the. See, I never use Euclidean metric. I never use balls, right? I never use distance. The only things I used was projection was continuous. Product had this universal property. So this was entirely an algebraic argument. So to check, my question is, if X and Y are topological spaces, and suppose that Y is not empty, is projection on X from X cross Y to X a quotient map? Yeah. Now you can pretend that this picture has this as X and this as Y and make the same argument, and then you'll realize that that argument is entirely arrow theoretic, so to say. Very, very algebraic argument. So this is exercise. I already made a concrete argument, but I hardly used any properties of R, right? Just as when Himanshu made his original argument here, Himanshu made his argument about diagonal being an embedding. His argument was use the projection, and that is identity. But his argument never used any properties of R, and so we took that same argument and made it work for anything. And that argument, you'll call this an algebraic argument, right? Algebraic style argument. There's no Yates equation. So same, this argument was also very arrow theoretic. Okay, so projection is a quotient map. Now I am going to ask you for one more example of quotient map. So this is a fantastic example. See, I keep saying, oh, this is the most important thing. But then there are all those very important things. Okay. Very important example. The very important example is this. I'm going to take a line, and that's going to be my X. And I'm going to take a circle, and that's going to be Y. So this is R, and this is S1. Now I'm going to define a map from line to circle like this. I'm going to arrange the line like a spring. Now this is a three-dimensional picture, and the line is not intersecting itself. This is like a spring. So Thindik has told us, write your maps vertically. So the map is going to go down from here into the second space here. This is spring. So this spring is just a copy of R, and this spring is a copy of S. And so I have this map of the spring going to. So in other words, the line is winding around the circle. The line is a thread. It is winding around the circle. This is the map. So now somebody give me a formula for this map. Here is T. Okay, T belongs to R. And here is X comma Y belonging to S1. And what should it satisfy? X square plus Y square equal to 1. Okay. Now I want to send t to xy. What should be the formula? Tell me the formula.
e to the power
So e raised to 2 pi I.
Wow, you guys have a complex analysis course going on side by side, but how about since I want a pair of real numbers, how will I write it?
So we can consider the components
Cos t,
cos t.
sin t.
Cos t and sin t. This is how it's going, right?
Mhm.
And it's going round and round and round and round and round. As you guys told me, the more sophisticated formula, this is t goes to e to the power pi it. Okay. Now this is winding with period 2 pi. After 2 pi, you are coming back. If you want to come back after distance 1, then the other form you will have to use another formula. Then you will have to say that cos 2 pi t and sin 2 pi t, or t goes to e to the power 2 pi I t. This looks pretty because then z goes into, z is the fiber over the point 1 in circle. Okay. So I have this map. Is it clear? So actually R plus is a group, and S1 multiplication is a subgroup of C star. So you write this a point here at Z with mod Z equal to 1, which means Z is equal to X plus IT, where X square plus Y square is 1. IY, where X square plus Y square equal to 1. X square plus Y square equal to 1 is the thing mod Z equal to 1. Okay. This is the same as this. Okay. So in that case, this map t goes to e to the power 2 pi I t is a group homomorphism. Is that clear? It's a group homomorphism. That's the basic property of the exponential map, that it converts addition into multiplication. So e to the power 2 pi I t1 plus t2 equal to e to the power 2 pi I t1 multiplied by e to the power 2 pi I t2. So this map, which I'll call as x. So x is a group homomorphism. Also, exp is surjective. So your first, second, third, whatever homomorphism theorem will tell you that R plus modulo kernel, and what's the kernel? Kernel of x. What is the kernel of x?
Integers.
Correct. So modulo kernel of x is isomorphic as a group to S1 with multiplication. This is what do you call it? Third law of isomorphism? What is it called? Fundamental theorem of isomorphism? Some such. Doesn't it have some name? You know, I was in college
Fundamental theorem
50
of
years
isomorphism.
ago, so I have forgotten. Yeah, what did it called?
The first theorem of isomorphism.
First theorem of isomorphism. In the category of groups. But now I am looking at it as topological spaces, and my claim is question. Take topological spaces R, S1, and the continuous map X from R to S. So of course, here I am assuming, is it continuous? Let's settle this little point before going on. Are you sure exponential is continuous? So this is where you use your complex analysis.
So here we have to consider S1 sitting inside the
Correct.
complex.
It has the subspace topology, right? That's how we
Hmm.
defined the topology of
Hmm.
S1 in the last
Okay.
lecture, recall.
Hmm.
Okay. So this map is continuous because the exponential map from C to C is given by a certain convergent power series whose radius of convergence is infinite. And so it actually defines a holomorphic or complex analytic map from C to C, therefore definitely continuous, and its restriction to these subspaces therefore is continuous. So answer is yes. And now the second question is, the answer is yes. Second question. Is X a quotient map? So what do I have to check? One, X is surjective. Is it surjective? Is X surjective? Every point on the circle can be written as cos t sin t. You see X and Y, you know this. This is how the point looks. This is X comma Y. And now this is the angle theta. X is equal to cos theta and Y is equal to sin theta. So theta goes to xy under this map, right? So it is surjective. Every point there is of this type. So this you know practically from your 12th standard onwards, that any point on the circle can be written as cos theta sin theta, with cos theta equal to x, sin theta equal to y. This has a solution in theta. Theta is cos inverse x and whatever, sin inverse y. Doesn't mean that there is such a thing. It's only a name, but this always works. So if you have studied your basic exponential function, you know that yes, it is indeed surjective. So tell me, what's the image if I take the exponential map from C to C? C to C, I take Z goes to e to the power Z. What is the image? Somebody tell me what's the image of this map? E to the power Z, as you know, is what? 1 plus Z plus Z square by 2 plus blah, blah, blah. Yeah? So what's the image of this map? Bolo. Hey, have I lost my audience? Are you guys there?
C
Yeah.
Yes,
minus
sir.
So what's the image?
C minus origin.
That's good. C minus 0. Image of equal to C minus 0. Why is 0 not there in the image? Because e to the power z times e to the power minus z is equal to e to the power z minus z is equal to e to the power 0 equal to 1. Therefore, this number e to the power z has a multiplicative inverse. 0 times anything can never be 1. So this is never 0. So of course the image is contained in C minus 0. But why is everything in C minus 0 the image? So I hope you can prove it. This is very important. You know, there's a book, there's a very, or I don't know how it is now. When I was in college, there was a very popular analysis book called Rudin's Real and Complex Analysis. And the book began by saying that this exponential function is the most important function in mathematics. And it went on to prove its basic properties. Okay, so perhaps that book is still there, it is still popular. I hope it was a nice book. Well, now in my old age, I'm not happy with any of the books almost, but doesn't matter. It's quite a nice book. So you go read the properties of exponential map there if you don't know them. And anyway, you have complex analysis course going side by side with this, and in which a lot of this is likely to be covered. Okay, so this map is surjective. What was the second property of, I have run out of time. Okay, let me finish this point and the second point I want to say is that V is such that X inverse V is open in R, then V is open in S1. This is also true. Both these things are true. Verify them. Exercise, verify. Verify. So I'm asking you to do a very simple exercise in calculus because the map is defined in terms of cos theta and sin theta. So I'm asking you to check some properties of the function sin and cos. Okay, and that shows that exponential map from R1 to S1 is a quotient map. In topology. So these were groups, and this was a quotient map in groups, but these are also topological spaces, and this is a quotient map in topology also. And the group structure and the topology structure are not independent. They are joined together in something called topological group, and this is actually a quotient map of topological group. So next time, next lecture, we will introduce topological groups. Okay, and then we'll also give lots of examples of quotients and whatnot, more and more examples, few definitions and lots of examples. The start of any course is heavy on definitions, and so you have to revise definitions with examples. Okay, I'll stop here. Any questions?